This video discusses the solution to question 32. Consider a CMOS logic gate, of which figure 4 shows an example. Assume that you want to try to design a combinatorial circuit which realizes a generic logic function. You might remember that it is always possible to synthesize a logic function using inverters and 2-input NAND gates, or inverters and 2-input NOR gates, or even with only 2-input NANDs or NORs. You will design the NAND and NOR gates by equalizing the on resistance of the pull-up and pull-down networks to the ones of the simple inverter. If your only aim is to minimize the area occupied by the realized function in an integrated circuit implementation, and assuming that the circuit area is uniquely due to the gate area of the transistor used, which choice would you make to realize the logic function? In the original question, this statement is followed by 8 possible options, but these can be split up into 3 sub-questions. Firstly, do you want to use NAND gates or NOR gates? Secondly, if we want to implement the inverter function, will we use inverters for that, or will we use a NAND or NOR gate for that? And finally, how will we choose the channel length of all of these transistors? And again, we need to answer these 3 questions with the aim of minimizing the overall area of the circuit. So let's first have a look at the 3 possible circuits. We have an inverter, a NAND gate and a NOR gate. The mobility of holes as a carrier is smaller than that of electrons, which means that if we want to get the same on resistance for the PMOS at the pull-up network or the NMOS at the pull-down network of the inverter, we should choose the width of the PMOS transistor to be larger than that of the NMOS transistor. As a result, the aspect ratio W over L for the PMOS transistor will be larger than the aspect ratio of the NMOS transistor, so P is larger than N. Now we can take a good look at the NAND and NOR gate. Let's first take a look at the pull-up network of the NAND gate. We see that there are 2 transistors in parallel, and either of these can be turned on at any time. If one of these transistors is turned on, we want to see the full on resistance as we would see in the inverter across any of these 2 transistors. So we want the same aspect ratio for the PMOS transistors in the NAND gate. The NMOS transistors, however, are in series, and we want to see the full on resistance across both of these transistors together. That means that we want to see half of that on resistance across each transistor individually. Therefore, we should choose the width of each of these NMOS transistors to be 2 times as large as for the original inverter, which means that the aspect ratio of the NMOS transistors in the NAND gate will be 2N as opposed to N in the inverter. Finally, we can discuss the NOR gate. Here we can use the same approach for the NAND gate, but then the other way around. So the NMOS transistors in the pull-down network can be turned on individually or both together, which means that either transistor will need to have the full on resistance of the NMOS transistor in the inverter. So therefore the aspect ratio of the NMOS transistors in the NOR gate will be N. The pull-up network in the NOR gate consists of 2 series PMOS transistors. We need to see the full on resistance, as we would see in the inverter, across both transistors together, which means that the on resistance across each transistor needs to be half that of the original resistance in the inverter. To do that, we can choose the width of the PMOS transistors in the NOR gate to be twice as large as that in the inverter. And therefore we will get an aspect ratio of 2p for the PMOS transistors. If we now want to decide between the NAND and the NOR gate in terms of gate area, we just have to look back at the given information from the inverter. We found that the P aspect ratio will be larger than the N aspect ratio. So from that follows that the NOR gate with its very large PMOS transistors will be much larger than the NAND gate. So we will choose for NAND gates when we want to optimize the gate area. Secondly, we have to ask ourselves if we want to implement the inverter function with normal CMOS inverters or with the NAND gate. This is quite a simple one to answer, because the inverter just uses 2 transistors with aspect ratios P and N, and the NAND gate uses 4 transistors with the aspect ratios P and 2N. Since we need to use 4 transistors for each NAND gate as opposed to 2 for the inverter, which are also larger than that in the inverter, it is much more area efficient to just use a CMOS inverter for the NOT function. Finally, we have to answer the question which channel length we should use. To minimize the area of the overall logic function, we can choose the channel length to be as minimal as possible, as allowed by the transistor technology. So in summary, we should choose NAND gates combined with inverters and a minimal channel length for all the transistors.